All right, I would say let's start. So our last speaker for today is Matthew Meglio, and he's going to talk about minimal dilations categorically. So I talk about dagger category. Again, you have 30 minutes for a talk and then 10 minutes questions will follow. Take it away.
Cool. Thanks, Paolo. As Paolo said, I'm going to tell you a story about minimal dilations of contractions. So this is a Hilbert space thing, but I guess the whole idea is to view these things in a category theoretic way, and we're going to see that the resulting universal construction we get actually has some other interesting examples, one of which I think is very closely related to what Dario spoke about in the first talk this afternoon. And then I'll sort of prove some general result that hold in some nice categorical setting about these minimal dilations. So to start, I think it's good to just warm ourselves up into thinking about Hilbert spaces and contractions. So, so a Hilbert space is, of course, a vector space equipped with a complete inner product. And this inner product sort of gives the vector space some abstract notion of geometry. So we can define lengths. So we can define the norm is some abstract notion of length. And the inner product otherwise encodes some kind of abstract notion of angle. So these are the objects that we're going to think about. And today, the morphisms of Hilbert spaces that we're going to consider are the contractions. So these are the linear maps between Hilbert spaces well, not going to denote by Hild less than or equal to 1. Okay, so amongst the contractions are the isometries, and these are the maps that preserve the geometry exactly. So they're defined to be the maps that preserve lengths, but by virtue of preserving lengths, they also preserve the inner product. And these, of course, form a full subcategory of Hild that I'll denote Hild 1. So with all of this in mind, the starting point of this talk is this thing called Nye's unitary dilation theorem. And it's a kind of structure theorem that says that it gives a way of expressing contractions in terms of isometries and unitaries in a universal way. And this theorem is very useful because it allows so in functional analysis, it's used to be able to extend things that functional analysts know about unitaries and isometries to contractions. And so it really was the starting point for the modern theory of contractions in functional analysis. So it's a very useful theorem. So what does it actually say? So it says that every contraction F on some Hilbert space X has a unitary dilation U on some Hilbert space S containing X. So the point is there's some isometry S from X to S. So that exhibits X as some closed subspace of S. And the dilation bit is the fact that if I sort of go via this injection, I do some power of U, and then I do the corresponding projection onto the subspace X. That's the same thing as doing that power of F. So somehow, so the action of U on S is containing the action of F on X. And this minimal condition can sort of be expressed in a few different ways. So one of them is that S is the closed span of, or the closed internal sum of the subspaces U to the n of S. So these are just the images of S under the nth power of U for all n from minus infinity to infinity. So this is one way of expressing what it means for S to be minimal. But it's not so category theoretic. Another way of capturing this minimality is via this universal property. So it says that if I have some other dilation T of F, then there should exist some isometry M that exhibits T as a dilation, like this V as a dilation of U. So this is more like like the kind of universal properties that we're familiar with. Okay, so we have this dilation theorem, and I'm going to massage it a bit into a form that I think is more amenable to category theory. So at the moment, this theorem is about sort of endomorphisms on a particular object, but really I'd like to be able to say something about arbitrary morphisms, so arbitrary contractions. And so I can't really, if I'm looking at an arbitrary morphism from X to some other object, then I'm not going to be able to do this power thing, this iteration. So let's just forget about that, and we're just going to consider just F and U by itself, and not worry about powers of F and U. And if we then look at what we've got, so if you look, there's composite U S star. So S here is an isometry, S star is a co-isometry. So this composite here is also a co-isometry. And so at this point, the function of U can just be absorbed into this S star, because we no longer need to take powers of U. So we can simplify things. And instead, what we're going to do is consider pairs of isometries from X to S. So we've got S1 here was the old S, but S2 now is what was the old S composed with that unitary U. And so now, and we do the same thing with our for our universal property. So now what we really have is we have a co-span of isometries that's dilating F. And then at this point, we can now make our change from just having an endomorphism on an object to having a morphism from one object to another. And this is essentially all the modifications that I'd like to make, but I'm going to redraw this diagram in a way that is maybe a bit more familiar to everyone. So this is a re-expression of the universal property. So the idea is, if I have some contraction F, the claim is that there's a co-span of isometries, S1 and S2, such that if I do S1 and then I do the adjoint of S2, that gives you F, such that whenever I have another such co-span, there should exist a unique isometry M that makes the relevant triangles in this diagram commute. And so if I have this kind of setup, then I'm going to call S1 and S2 a co-dilator of F. Now I put the co there because it seems like a co-limity kind of construction. You could imagine I could have done the whole story with all the morphisms reversed just by taking the adjoints of everything in terms of co-isometries instead of isometries, and then I'd get what I would call a dilator of F. And of course, co-dilators and dilators are equivalent notions just by taking adjoints. But in this case, I've defined a co-dilator of F. Okay, so we can do all of this within the category of the Hilbert spaces and contractions. But of course, I think it's good then to take a step back and see if we can generalize further. So this notion of co-dilator that I defined on the previous slide actually makes sense in any star category. So here by star category, I mean the same thing as a dagger category. I'm just using the star for more consistency with some other functional analysis notions. So in particular, it's a category equipped with this operation that sends every morphism F from X to Y to some morphism F star from Y to X that satisfies these axioms. So the first axiom, the first two axioms say that this star operation forms a contravariant functor, and this third axiom says that this contravariant functor is involutive. So in this abstract setting of star categories, we can define what it means to be an isometry. So a morphism F is isometric if F star F equals 1. And of course, in the category of Hilbert spaces and contractions that I talked about before, the isometric morphisms are precisely the isometries as one would normally define them. And so sort of what I explained on the previous sort of leading up to this, the previous couple of slides, is that every morphism in this category of Hilbert spaces and contractions has a codilator. So it has a cospan of isometries like this, that's universal in the sense that I described before. Okay, so I've introduced this new universal construction of a dilator or codilator, depending on the perspective you want to take. So the next sort of part of my talk is I'm going to introduce some other categories which have dilators or codilators to give you a bit more of a flavor for what these things are. So for the first example, we're going to consider these things called partial bijections. So a partial bijection is an injective partial function between two sets. So here I have a set with 4 elements and a set with 3 elements, and F is well, it's a relation between these two sets, but it's a partial bijection. So it's yeah, it's an injected partial function. So I don't know what more to say there, but the point is that these partial bijections form a star category. So the adjoint operation is just the transpose of F as a relation. So it just makes the mapping go the other way. And in this star category, the isometries are the totally defined maps. So these will be the injective functions. And so the codilator of F is quite easy to picture. So what you do is you take, say, the morphisms that are on which F is, sorry, you take the elements on which F is defined, because they're the ones that are going to be sort of common in the domain and the codomain of F. And then you take all of the leftover elements of the domain and the leftover elements of the codomain, and you just put them all together. So the injection here maps these elements to these elements, and the injection here maps these elements to these elements. And it should be pretty clear that if I do this injection, and then I do the adjoint of this injection, I recover F. And I mean, you can go away and think about it for a moment, but this cospan of isometries is minimal in the sense that if I have some other cospan of isometries which dilates F, then there's going to be a unique injective function from this apex into the apex of the other cospan. So this universal property uniquely determines this codilator of F. Okay, so that was the first. Well, I guess it's the second example, because the first example was Hilbert spaces and contractions. For the third example, this is where now you're going to see some connections to Dario's talk. So we're going to consider the category of finite probability spaces and stochastic maps. But actually, I'm going to restrict attention to those finite probability spaces with full support. And I think Dario actually mentions, I can't remember the name he used for this, but this came up in Dario's talk as well as a way of sort of avoiding the need to talk about the almost sure equality of the stochastic maps between these things. Anyway, so this is the category we're going to consider. So here's an example of a morphism in this category. So the objects here, they're probability spaces. So they're sets. So this one is the set XY equipped with like a probability measure. And this one is the set ABC equipped with a probability measure. And the map F from this set to this, sorry, from this probability space to that probability space. So it assigns to every element of the domain a probability distribution, or sorry, a probability measure on the codomain set, such that essentially like the law of conditional probability holds. So the probability of A is the sum of the probability of X times the probability of A given X plus the probability of Y times the probability of A given Y. So you can see that a half times a third plus a half times 2/3 is a half, and so on like that. So this category is actually a star category where the adjoints are given by the Bayesian inverses, which again was something that Dario talked about. So here's the Bayesian inverse of F. So the way you compute F star is you sort of go, well, the probability of X given A will be the same thing as the probability of A given X times the probability of X divided by the probability of A. And you can use that formula to compute all of these probabilities. So this operation that sends a morphism to its Bayesian inverse is it satisfies the axioms that make this into a star category. And then the point is that every morphism in the star category has a dilator. So in this case, I'm going to talk about dilators rather than codilators because it's easier to think about co-isometries rather than isometries. So the dilator of F is depicted here. And it's I guess it's the joint distribution. So what you do is you take the pairs. So you take pairs of elements from the domain and the codomain such that when you sort of apply F to the element in the domain, the corresponding probability here is non-zero. As recall, we're restricting our attention to the things with probability, with non-zero probability. And then what you do is the probability that you assign, say, to the pair XA is just the product of the probability of X and the probability of A given X. So you do that and you get this probability space. And the span of co-isometries, so I should say first what a co-isometry in this category is, although I think Dario mentioned that as well. So a co-isometry in this category is a deterministic map. So this span just consists of essentially the product projections, if we were regarding this, I mean, it's not exactly the product, but it's some subset of the product. But it's essentially you take those projections as functions, but regard them as deterministic maps between these probability spaces. So it would send the pair XA deterministically to X, and the pair YA here would be mapped by this one deterministically to A. So the claim is that this span of co-isometries, again, satisfies the universal property that I depicted, or at least the jewel of that a couple of slides ago. So if I have some other span of co-isometries, such that if I do the star of the first one and then the second one, I get F, then there should be a unique co-isometry that sort of mediates the two spans. So I think that's quite interesting. So this, I guess, is also related to the Alex Simpson's notion of an independent product, but in some sense, rather than taking the particular spans as some kind of structure on a category, we're in a more specialized setting. We're in a star category, and then what we've done is we've just sort of defined the don't know what I'm trying to say, but this maybe even gives you an example of an independent product relative to F or something like that. I have to think about that more. So I have to thank Paolo for pointing me to this example. And there's this paper called The Information Loss of a Stochastic Map, in which this particular factorization of F is called the Bloom-Street factorization. As far as I can tell, that's not like a general name that's used across probability theory or something. The only paper that comes up when you Google it is this one, but that's maybe a further reference of interest. In any case, so this is another example of a star category that has dilators of all morphisms. Okay, so I've now introduced this new universal construction, and I've given you a few different examples of star categories where every morphism has a dilator. So I'm going to end my talk by focusing on some abstract setting of nice enough star categories where I can prove a variance of Nye's dilation theorem. So this setting is the following. So it's we're going to consider a star category C with an enrichment in abelian groups, finite ortho-isometric biproducts, and isometric kernels. So what does this mean? Well, I think enrichment in abelian groups should hopefully be familiar, but it just means that every Hom set has an addition and a zero, and these form an abelian group, and they respect the composition in the appropriate ways. So finite ortho-isometric biproducts, these are also called finite dagger biproducts if you're using dagger category terminology. These are byproducts in which the injection maps are the adjoint or the dagger of the projection maps. And so what that means is that the injections are all isometries and they're orthogonal to each other. And finally, isometric kernels are just kernels that are isometry. So really what the condition is that every morphism has a kernel that is an isometry. And here it's every pair of objects has a byproduct that is ortho-isometric. So this is the setting. Now you might ask what categories satisfy these conditions. There's a number of them, but for today, the only one I'm going to tell you about is the category of Hilbert spaces and all bounded linear maps. So this is not Hilbert spaces and contractions, but it's Hilbert spaces and all bounded linear maps. Okay, so this is the abstract setting. Now, I've got to make this definition. So a morphism F from X to Y and Z is a strict contraction if 1 minus F adjoint F is equal to G adjoint G for some isomorphism G. So I could have first defined the notion of contraction and then told you some things about contractions, like they form a star subcategory and all this other stuff. But in the end, this dilation theorem in this abstract setting, I only know how to prove for strict contractions. So we're just going to focus on the strict ones. So I should say that strict contractions don't form a subcategory. And if you sort of want to think about what a strict contraction is within this subcategory of Hilbert spaces and bounded linear maps, it's a bounded linear map whose operator norm is strictly less than 1. So in particular, it's a contraction, but it's a contraction that's strictly contractive in that sense. Okay, so the claim is in such a star category C, every contraction has a codilator. So how do we prove this? Okay, well, the first thing is we're going to start by constructing a dilation of our morphism F. So if I have a strict contraction F, well, here strictness is not so important. I have a contraction F. I can take the product pairing of F with this morphism G, and that gives me a morphism from X to Y plus Z, and I can consider that together with the injection of this byproduct, the first one, and you can check that if I do this morphism and then the adjoint of that morphism, I recover F. And also this condition here means that this morphism here is also an isometry. So if I do this morphism and then adjoint, I get 1. Okay, so I've got this dilation of F, and now I want to produce a minimal one. So what I'm going to do is I'm going to take its jointly epic isometric factorization. So how do I do that? Well, I start by looking at the ortho-isometric byproduct of X and Y, and the unique comparison map here that makes the diagram commute. And then I'm going to factor this map. So I can factor it because I have these isometric kernels. So essentially I take the co-kernel of this map and then the isometric kernel of this map. And then the unique comparison morphism here you can show is actually an epimorphism. So that's what I'm going to do. And then I'm going to compose this epimorphism with the injections to get another co-span, which I'm going to call S1 and S2. And at this point, I can use the fact that this morphism and this morphism are both isometries to show that S1 is an isometry. And similarly, I can show that S2 is an isometry. I can also show that if I do S1 and then the adjoint of S2, I get F. So what that means is that S1 and S2 is another dilation of F, but in particular, it's a jointly epic one. So at this point, I can forget the code span that I started with, but I now need to show the universal property. Okay, so let me take, so I've got T1 and T2 are isometry such that if I do T1 and then the adjoint of T2, I get F. And I'm also again going to consider their co-product co-pairing, T like so. And so at this point, I need to use the fact that G is an isomorphism, the fact that we have a strict contraction. So let's do some calculation. So first thing is I can compute, if I do T star, or I do S star, I can, this is a map from X, the byproduct of X and Y to itself. So I can sort of work out what its matrix components are. And in both cases, we get the matrix 1, F star, F, 1. And it turns out that if we ask that 1 minus F star F be invertible, then this matrix here is also invertible. So its inverse is given by this formula here. And so if this morphism here is invertible, well, that means that S is actually a split monomorphism, but it's also an epimorphism. So S is an isomorphism. So its inverse is going to be given by doing the adjoint of S and then the inverse of S star S. So what that means is, if there were a morphism here that made this diagram commute, then it ought to be the inverse of S followed by T. And indeed, you can prove that if I do that, then I actually have an isometry. And that uses the fact that T star T equals S star S. So this is the unique comparison morphism that makes the diagram commute. And that completes the proof. So every strict contraction has a codilator. Okay, so this is essentially where I'm going to end the talk. But to summarize, so I introduced this new universal construction that I've called a dilator or a codilator. And this universal construction is inspired by the minimal unitary dilation of a contraction, but it also includes things like this Bloom-Schriek factorization of stochastic maps. And I gave a proof that every strict contraction in a nice enough star category has a dilator. So that's where I'm going to end. So yeah, thank you for your attention.
All right, thank you for your talk. Thank you, speaker. All right, any questions? Feel free to unmute yourself. Maybe I'll start with one to break the ice. So does this give a factorization system on the Dagger category?
That's a good question. So it is not an orthogonal factorization system, as far as I can tell. It doesn't, like, for instance, when you have an orthogonal factorization system, the factorization is unique, right? But this is more like a universal factorization in some sense. But I think it's not, like, it would be nice to know if there was some other notion of factorization system with which this kind of fits, like this fits in, but I don't know what that is. I guess another similar question related to this is, could you define a notion of dilator in an ordinary category? Like, what would that look like? And I think there you might also have to swap perspectives from this like co-product or product-like perspective to one of like some kind of minimal factorization with respect to two classes of morphisms or something like that. But it's not without like some concrete examples to really guide me in terms of how to make that definition. Like I could come up with some definitions that sort of work, but like, I mean, unless you have examples to sort of instantiate them, there's kind of no point. But yeah, this is a good question. Yeah.
Well, it's kind of unfortunate if it's not orthogonal, since it kind of is about orthogonality in the sense of geometry. Like, I feel like this would be more orthogonal than anything that's actually orthogonal system. But anyway, any other questions? Right. Doesn't seem that there's